Okay, everybody, we're looking at human hearing today. So I just want to review the human ear and its different components. So we're going to start by looking at the external ear. This is the pinna, or external ear, which focuses the sound waves into a small auditory canal, which then channels the sound into the eardrum. The eardrum vibrates, and then the vibrations amplified by about 30-fold through three bones called the hammer, anvil, and the stirrup. And they increase the vibration, and they transfer it onto this little structure, looks like a snail, called the cochlea. In here we've got a variety of nerve endings that detect those various frequency vibrations, and those vibrations are ultimately sent on to the brain through the auditory nerve.
Why do we need a brain? To interpret the impulses. That's right. I just happen to have an auditory nerve right here in my pocket. And I've got the brain. Okay, so we connect the cochlea with the temporal lobe of the brain. We should be able to hear them.
Right. We have sound reception, conduction of nerve impulse, and interpretation by the brain.
Great. Let's take a look at this one more time.
Sound waves are vibrations that travel through gases, liquids, and solids. When these vibrations reach the outer ear, they travel along the ear canals of the eardrum, causing it to vibrate. The vibrations are then transferred to the hammer, anvil, and stirrup. As waves of sound travel from the eardrum to the stirrup, they are intensified about 30 times. The stirrup passes the vibrations to the membrane on which it rests, the oval window. Vibrations are then transferred to the fluid-filled canals within the cochlea. When the oval window moves in, the round window moves out to equalize the pressure in the cochlea. In this illustration, the cochlea is uncoiled to show where sound waves of different frequencies, or pitches, are detected. High-frequency sounds are detected close to the oval window. The low-frequency sounds are detected towards the narrow end of the cochlea. A cross-section of the cochlea shows that the three fluid-filled canals are separated by membranes. The basilar membrane contains sensory hair cells with cilia that extend to the tectorial membrane. As vibrations travel through the fluid, the basilar membrane moves up.
And you can see here how the energy is transferred onto the brain through the nerves that lead up to the auditory nerve. Okay, now the next thing we'll be looking at is human hearing range. When you look at the human hearing range, think of 20/20. You got 20/20 vision, you've got about 20/20 human hearing range as well. So the lowest sound we typically hear is around 20 hertz, and the highest is around 20,000 hertz, which gives us a tremendous range of hearing. However, that's a human hearing range. Other organisms use much, much lower frequencies. These would be organisms such as elephants that use their feet and the base of the tip of their trunks to listen to long-range sounds that are lower than 20 hertz in they're transmitted through the soil. We also have ultrasonic sounds that are higher than 20,000 hertz. These are really, really high frequencies we can't detect, but many other organisms such as bats, dolphins, porpoises depend on those for echolocation. They're using them to find their prey or to evade organisms that might be eating them. They're predators. Now, something else we have to be mindful of is something called sound intensity. Now, sound intensity is measured in decibels. A decibel is a tenth of something. So we use this special scale, it jumps in tens, and it's a logarithmic scale, which means that every time you jump 10 decibels, you're actually multiplying by 10. So for example, the difference between 10 and 20 decibels is tenfold. The difference between 10 and 40 decibels is actually 1,000. So we jumped 1, 2, 3 times. Each jump is a tenfold increase. So 10, 100, 1,000 times. So keep that in mind when you're calculating or determining sound intensity levels between objects. And here's just an example of the decibel scale. So the quietest sound that's possibly detected is very, very low energy. It's in the range of, think of a meter squared, 1 times 10 to the negative 12 watts, which is hardly anything. It's incredibly small. And the largest sound we can comfortably hear, like hear without significant damage, would be around 110 to 120 decibels, which is around 1 watt per meter squared. So we're looking at, oh my God, what is this? It's 1 to the 10 to the 12th range in energy levels associated with hearing. So a typical classroom like we're in now would be around 1 times 10 to the or around 40 decibels in sound. If you're in the hallway during a change, it might be around 60 to 70 decibels. So we're looking at about 100 to 1,000 times difference in sound levels between a quiet classroom and a busy hallway during a classroom transition. And this is just something to keep in mind, that our hearing is precious and it can easily be damaged. So you have to be mindful of that and try to avoid damage so you'll have good hearing throughout life. And it's just a little graph showing you an isolated tribe, how their hearing doesn't decrease very much with age, just a little bit. Non-noise exposed North Americans, this would be just background sound, there's quite a bit. And if you're exposed to a lot of noise because of your headphones or your environment, it's a significant decline. So you just kind of have a sense of your hearing and how it decreases with age and how sound in the background can cause damage over the long term. So that's it for this segment on hearing. Again, use your textbook to review and answer the associated questions. Take care. It's okay.